All right, friends and neighbors, welcome back to part 2 of chapter 14, WAN architectures. And so in this one, as the RFC snippet would indicate, we're going to do some security stuff with VPNs. So in part 1, we covered, characteristics of network topology architecture in the WAN. So we did Metro E and MPLS. This time we're going to do remote access and site-to-site VPNs, specifically with IPsec, and we'll talk just a little bit about TLS, and we'll redo the do I know this already questions. So if we jump all the way down to the key topics bottom here, we got concepts of site-to-site VPNs with IPsec and GRE. Now, in association with that, we'll talk a little bit about some of the access technologies that you have for the WAN, and then we'll compare, site to site and remote access VPNs. And then I got a little surprise at the end for you. So virtual private networks. Okay, what are we talking about here? Now we know that if we start thinking about the internet as a whole, it's really just a bunch of hosts or businesses, customers that are connected to the internet. Well, how are they connected? They connect to their ISPs, and then ISPs connect to other ISPs, which gets you to customers. So to get from, say, here to your favorite website, you would go from your machines to your ISP on up to larger and larger ISPs, and then down finally to wherever your favorite website is being hosted. So that sort of constitutes the internet as a whole. Now, sometimes we wish to protect the data that flows over the internet. So if you're sitting at Starbucks, or if you are just connecting wirelessly at any place, or you're in a site that you're not familiar with, you're at a conference, something like that, we want to protect our data. Well, unlike the MPLS VPNs that we talked about previously, the internet VPNs encrypt the data. So the concept of privacy can be thought of a couple of ways, and we talked a little bit about this last time, but privacy might mean that you have internet roads that are only for you, virtual circuits that are only for you, and that's the MPLS approach. Well, customer-based VPNs or internet VPNs, they take a different approach. IPsec and TLS encrypt the traffic so that even if somebody sees it, well, it's encrypted and they can't do a whole lot with it. And as we mentioned at the top, there are generally two flavors of VPNs that we set up, either site to site, where you got site A and site B, and we're going to encrypt between the two sites, and the clients don't have any idea that encryption is going on, or you can spin up a client server connection to an IPsec or a TLS server, and then that's our tunnel endpoints, and then the server will detunnel your traffic for you. We'll talk a little bit more about that in a second. So one of the cool things about VPNs is that they're IP based, right? We're talking about IPv4 and IPv6 networks, and so they're independent of the connectivity. So it doesn't matter what you got going on at layer 2. It also doesn't matter how you connect to the internet. You can have any one of a wide variety of connection types, and as long as we're talking about IP packets, well, you can encrypt them with the standard set of VPNs. So all of the technologies that are on this slide all share some ideas, right? So if we take a look here, we've got a couple of PCs that start off our connections, and whether they're wireless or wired, it doesn't really matter. You go out through your home gateway. And then you've got a modem of some kind. Now, this might be a DSL modem, in which case there might be another port here for a phone, or in this case, it's a cable modem. So when the coax or the cable connection came in, there was a splitter that sent one connection to your TV and then one connection down to the cable modem. So these two signals are exactly the same, but the cable modem's job is to pick the channel or the frequency necessary for data. So DSL does the same thing. So instead of being, cable, this would be a DSL modem here, and the phone would have access to certain frequencies, and the data connections would have access to other frequencies. So digital subscriber line uses existing phone lines, but the data connections or the data channels use different frequencies than the ones allocated for voice. So in a voice transmission, those very low frequencies for voice are in the range of 0 to 4,000 hertz, and so that's where we start. And that's what telephone circuits are based on. Now, the minute we say if we're talking about dial-up networking, your data use that exact same set of frequencies. And that's why modems, at the time, dial-up modems, they had a carrier wave frequency that was very commonly 1600 or 1800 hertz, somewhere in there. But DSL modems go higher. They pick frequencies that are above those normally allocated for voice. And so in that way, we can not only have voice and data going on at the same time, but we have more frequencies to allocate to data. Now the DSLAM, or the DSL multiplexer, separates these frequencies into ones that are being used for data and ones that are being used for voice, and so they go different ways. And that means that if you were going to do DSL, both ends of your connection had to be provisioned for DSL, which meant that the subscriber line card in the central office had to be able to do DSL, and you had to have a DSL modem. Cable internet is the same thing. It uses existing coax television lines, right? So the same coax connection that you use for TV, but the data frequencies or the data channel is a different channel than was used for TV. So here in the splitter, right, we send all these frequencies to the television or to the set-top box, and it tunes into a particular frequency and then demodulates the data. Well, your cable modem does that, but for a channel that's allocated for data. Now, coax is a much better medium than phone wire, and so we could get more capacity, more data, more throughput than we could with DSL. And because the medium was so much better, you could do a much greater distance. Now I'll jump down to fiber here for a second. Fiber strands, this is probably one of the newest technologies. Actual fiber strands to your home or business. Now this is what I just converted to. So I just went from coax to fiber. It's fabulous, by the way. And it's often Ethernet running over that fiber, just like we talked about with Metro E. Now fiber is a much better medium than cable. And so it can go farther distances, but also much higher capacity. So it's non-copper media in this case. Now I would be remiss if we didn't mention all of the advances in wireless internet. Certainly from your phone, we've been able to do 3G, 4G, LTE data, all the way on up to 5G. And around the corner, lots and lots of research into 6G. What's next? And wireless carriers will be eventually provisioning their networks for the advances that 6G represents. So we've been able to do that from our phones, but now, of course, they sell internet service. So you can put a box in your home that connects out to the cellular carrier in the same way that your phone did. So cellular system being used not just for voice or data from your phone, but also internet home use. Now, the thing that these all share is that they're access technologies. They're how you connect to the WAN. And you can have any one of these and still do VPNs over them. So private WANs, like MPLS connections, protect your data by ensuring that it's sent to the right place and that the virtual connections are yours alone, the virtual circuits. But what if your connections were shared or running over the public internet? What if you didn't have a virtual circuit just for you? And that's where internet VPNs come in. Now, the basic idea, the thing that we're trying to do here is ensure CIA, confidentiality, integrity, and authentication with anti-replay. So the easy way to remember this is with CIA. He doesn't do it this way in the book, but this is the way that I always remember it. So C is confidentiality, and the way that we ensure confidentiality or privacy is via encryption. Integrity of the data, or data integrity, is usually done using some kind of message authentication code. So this is just a calculation on the data, and that code or that calculation result is sent along with the data, and at the receiver you redo the calculation to see that if there's anything changed. So checksums are an example, MD5 sums are an example, and so a lot of technologies have similar data or packet checks. Authentication is the A, and that's for authentication for legitimate users. So most of these connections also have a username and password that you use to log in. And then finally, a lot of times we have a counter. or we keep track of the data that's been sent so that the packets that you've sent can't be used in replay. So let's say that you logged in somewhere and a bad guy caught that traffic and then tried to use those packets again later to log in. Well, anti-replay prevents that from happening. Now, all of this stuff with a VPN, all of this encryption, all of this authentication, all of this data integrity is accomplished between two devices that decide to set up a tunnel. And so the tunnel is the part of the connection that we say is encrypted. All right, so for the purpose of this slide, if we take a look right here, we can see that these two routers are the tunnel endpoints, right? And so the IKE exchange here, the Internet Key Exchange, the encapsulation security payload, that's encryption. So all of this is happening between the two tunnel endpoints. So the tunnel itself is what ensures confidentiality and integrity of the data, because the encryption starts and the encapsulation starts here at the beginning of the tunnel, and then we say it's been detunneled here at the other gateway. So the tunneling and the detunneling refers to the encapsulation of the data in a new header that handles all of the stuff for whatever VPN technology you happen to be using. All right, so let's talk a little bit more about site-to-site VPNs. Now, it turns out that the example in the previous slide and this example are site-to-site VPNs. So if you think about this set of hosts over here, the one network, and then we've got this other set of hosts over here on the two network. So the router on the edge of both networks is doing all of the encryption. These hosts have no idea that there's a VPN going on, that there's encryption going on. So from one site to the other, everything goes over this encrypted tunnel. Now, this happens to be IPsec, or IP security, and there are a whole bunch of RFCs that go along with IPsec. It's all the different modes of how it operates, all of the different algorithms that can be used to encrypt, etc., etc. So if you want to get started with the architecture, RFC 4301 is a good place to start. So the routers on the edge of each location encrypt all the data between the two sites, and again, the client computers are not involved at all. So IPsec then facilitates or provides the architecture that facilitates the sessions, right? When we establish a connection, we call that a session, and for that session, you have a key. And so the two sides need to get the key. We need to authenticate the two sides. And then, of course, we end up encrypting and doing the message integrity checks and everything else. So they connect. We establish a session key while they're connected. And then the sender will encrypt with the session key, or also called the shared key, because both sides are using the same one. And then the sender encapsulates the data in some kind of header, in this case, an IPsec header. And then it goes to the other router. And that router detunnels it, which means that it removes the header and decrypts the data and then passes it on to the end hosts. Importantly, for site-to-site VPNs, the end hosts are not on the internet, they're inside the organization. So now remote access VPNs with TLS. So TLS is transport layer security. So in the absence of a site-to-site VPN, so you don't have that architecture that we talked about earlier, clients can establish their own VPN. So here I am sitting at my place and I can VPN into work using a client server connection. Now previously this would have been done with IPsec as well, but because of the popularity of transport layer security and because it works so well, that the VPN clients today are transport layer security clients. So this is why we see a lot of traffic over 443. Now this is the same port that's used by HTTPS or your secure connections for the web. Now this was previously known as secure sockets, but that's been deprecated in favor for the advances seen by TLS. So it's the exact same technology that your web browser uses when it connects to a site using HTTPS. And here I've got an example where we've got this client down here, and we've got an organization on the left hand or the right hand side, I think, as you're viewing it. So from our router 0 to the right, all of this stuff would constitute the organization. And maybe this is a a server or a resource that we're trying to get to. So PC1 would establish a VPN tunnel to the VPN server. And so across the internet then, this connection would be established. And when it gets to the VPN server would detunnel the traffic and then send it on to the resource that we were trying to access. Now, importantly, if you were trying to go to a site on the internet, you would not go to the VPN server. You would just go straight to that site. Now, what follows is not part of the chapter, but I think it's an important thing to realize that because we're setting up a tunnel, there's a whole bunch of things that happen that are not readily apparent. So we've said now, okay, we established a tunnel. We've said that when we're going to go to anywhere into the site of the organization, we're going to encrypt it. And when we're not going to go to the site, we're not going to encrypt it. Well, that also means that you have to have some sort of understanding of this network back here, don't you? Instead of just using your default gateway. So that means that your host routing tables have to change. So what we've got right above me here is my routing table that I had before I established my VPN connection. So I've just got one network that I'm dealing with here, the 18 net, right? And a very, very small set of routing table entries. And on this side over here, this is the routing table that appears once I establish my VPN connection. This is crazy. So look at all of these entries, and this is just a partial snippet. Note that these entries, we haven't even gotten to those yet. These are just all the way, they're all the way down at the bottom of this routing table. And all of this stuff was specialized routes that were added by my VPN client so that I would know, A, when to encrypt and when not to encrypt, and B, how to get to the resources that are on the inside corporate network. And so that's why you see all of these RIT networks over here. So I actually have a presence on the RIT network. So this is important to realize that it's not just that you encrypt traffic when you're going to send it. You have to have routing table updates that tell you when you're supposed to encrypt and where those destinations are. And here's an example of a TLS, or a transport layer security packet. We've got the destination port 443 here, and then here we see encrypted application data. Now there's a lot more data here than this little snippet shows, but the important detail here is that at this point it's encrypted. And so the Wireshark doesn't understand it. It can't read it because, well, it can't decrypt what this data is. Well, there you go. I hope that gives you some insight into what your VPN is doing. It's not just about encrypting and setting up a tunnel. It's about changing your routing tables, forwarding packets over encrypted tunnels when you need to, and then changing actually the packet structure that you're sending. All right, this is a reminder of the "Do you know this already?" questions. So we did a lot of these last time, but we'll do them again, and then we'll cover the VPN ones at the end. Question number 1, which of the following topology terms most closely describe the topology created by Metro Ethernet tree service? Well, remember that Metro Ethernet tree service is not full mesh, and it's not point-to-point, so that was BNC, hub, or spoke, or partial mesh. Question number 2, which of the following is the most likely technology used for an access link on Metro Ethernet service? Remember that Metro Ethernet is likely going to be fiber, and so we need to see these sort of LX abbreviation. So that was A. Question number 3, an enterprise uses Metro Ethernet WAN with Ethernet LAN service with the company headquarters plus 10 remote sites connected to the service. Now remember what kind of connections the LAN set you up with. The enterprise uses OSPF at all sites with one router connected to the service from each site. Which of the following are true about the layer 3 details most likely used with this service and design? Choose 2. Well, the WAN will use one subnet because we are talking about Metro Ethernet, and the routers will have greater than or equal to 10 neighbors because remember this was the mesh connection. Question number 4. An enterprise uses an MPLS layer 3 VPN with the company headquarters connected to 10 plus remote sites connected to the service. The enterprise uses OSPF at all sites with one router connected to the service from each site. Which of the following are true about the layer 3 details most likely to be used in this service and design? Choose 2. Well, remember that in this case, we start off with the customer edge stuff and the provider edge stuff, and that's your only neighbor. And so now, even though you got a bunch of sites, they only have one neighbor each. So B and C, the WAN will have 10 or more subnets, all of those connections with those neighbors, and the routers will have more than one, or will have one neighbor. So the reason it's 10 or more subnets is because if it was one subnet, you would have a lot more neighbors. Question number 5, which of the following answers is most accurate about access link options for an MPLS network? And that's D, uses a wide variety of L2 or L1 and L2 technologies. This is just like any VPN technology. It doesn't matter how you connect. You can use anything you want because we're talking about MPLS, which is above all of that stuff. Question number 6, an enterprise connects 20 sites into an MPLS VPN WAN. The enterprise uses OSPF or IPv4 routes at all sites. Consider the OSPF area design options and the provider edge to customer edge links. Which of the following answers is most accurate about the OSPF areas and the provider edge, customer edge links? And that was A, the provider edge, customer edge length may or may not be in area 0. And again, this was not really covered very much in the chapter, but you can build your OSPF topology any way that you want to. And because you're now connecting to the provider network, the provider will do their own thing. And so you can choose to extend area 0 out to the provider edge or leave it at the customer edge. Question number 7, a colleague mentions using remote access VPN. Which of the following protocols or technologies would you expect to have your colleague to have used? Well, we talked about site-to-site VPNs being IPsec. And historically, the client server might have been IPsec as well. In fact, in the last video, I think I said that all the ones that I've used historically have been IPsec. But as we know, the chapter goes on to say, well, look, today we're doing TLS, so that was A, transport layer security. Chapter 15, look ahead. We're getting close. I think there are only 19 chapters in volume 2. Chapter 15, look ahead, cloud architecture. So we'll be talking about the networking components, or the network components and the servers in a cloud architecture. And cloud architectures are all about virtualization, or what we sometimes call server virtualization. And then we'll also talk about public and private clouds. What's the difference? And then the WAN pathways to the cloud. This will be the WAN pathways to the public cloud. And then, of course, you can build your private clouds inside a public cloud, but that's a little more complex than we actually need. But there we go. That's our Chapter 15 look ahead. All right, this was the second part of Chapter 14. This was virtual private networks or internet VPNs. So today we talked about site-to-site VPNs, a client server, the technologies IPsec and TLS. And of course we reviewed the connections, DSL, cable, wireless, and fiber, right? It doesn't really matter what kind of connection that you establish to the WAN because it's all IP-based anyway, and these VPNs, whether you're doing IPsec or TLS, both run over IP packets and the standard set of protocols. So it doesn't matter how you got there, you can still encrypt and protect your data. Well, like and subscribe for the journey to the cloud. May those packets always reach their destinations, no matter how you decide to encrypt them. And hey, this is CCNA. You can do this. We're on to Chapter 15, Cloud Architectures.